Hello, everyone. Here in this video, we are going to talk about a theorem called Bernoulli's theorem, deals with deals with fluid dynamics. The theorem is a kind of a conservation of energy concept, which says that there are certain conditions, like we have said for the equation of continuity in the other video, the same conditions like for a incompressible. When you say incompressible, its volume is fixed, it cannot be compressed, and hence density is also constant. Non-viscous, other condition. Non-viscous means we are not taking the viscous forces that gets into the picture, and we are assuming like it's not having any viscosity. The streamlined flow. Streamlined flow means all the particles crossing a particular point in the stream will have the same velocity. In that case, if we have a fluid that is incompressible, non-viscous and streamlined flow, the Bernoulli's theorem says that the sum of potential energy, kinetic energy, fluids, because they have energy, they have some energy that's relevant to the pressure because there is a pressure difference, and the pressure energy. The sum of potential energy, kinetic energy, and pressure energy per unit mass. Of course, once it is constant per unit mass, it is constant for the entire mass also. But theoretically, it's being proved per unit mass. So Bernoulli's theorem says the sum of potential energy, kinetic energy, and pressure energy per unit mass for a incompressible, non-viscous, streamlined fluid is always constant. One energy increases, other energy decreases. Before going into the details of that, let me prove it quickly. I'm not proving it in a very big detailed way, but I'll quickly prove what it meant to mean by, right. So let's try to prove what is Bernoulli's theorem is. Let us consider a fluid flowing this way. Here, assume that it's having an area A1. Here, area is A2. We have taken in such a way it's very clearly that A1 is greater than A2. Let the fluid is entering with a velocity v1. Let it is coming out with a velocity v2. As per the equation of continuity, area into velocity at any point remains constant. As a1 is greater than a2, it's obvious that v2 is greater than v1. From a reference point, there at a certain height, let that height is like this. From a reference point, the height is h1 and h2, such that h1 is greater than h2. Then here respectively there is a pressure P1 and here is a pressure P2. Obviously, as height is more, pressure at that point is also more due to the reference point. P1 is greater than P2. Let here the density is ρ1. Though symbolically I am taking it like ρ1 and ρ2, both are same because we are anyway handling about an incompressible fluid whose density is constant. You take all these things into consideration. For this liquid, I want to prove between these 2 points, between this point x and this point y, total energy of the system remains constant. That's what I want to prove, right? So let's prove these things one by one. Let us say at point x, that means this point you're talking about, the pressure energy is, you want to calculate pressure energy. We can simply write work done formula like force and displacement, but we will write this force in terms of pressure, as pressure is defined as force per unit area and force is pressure into area into displacement. So displacement can be written like velocity v into dt, assuming like that fluid flow is happening in a time dt, and at the same time dt something else is happening at the other point y. So at the point x, all these things becomes p1 a1 v1 dt because they're all parameters of ones. Where at the point y, the same value at y, pressure energy becomes P2 A2 V2 D. That implies between the points X and Y, work done due to the pressure difference, pressure energy difference is the difference of them. P1 A1 V1 dt minus P2 A2 V2 dt. This is one part that we want to prove, right? Let us try to prove the other part now. Between points, the same points X and Y, potential energy difference is mgh is the formula for potential difference, but in a small time dt, the m that's flowing through the point x is assumed as only dm. It implies dmgh1 minus dmgh2. So there are two works done due to the pressure energy and the potential energy difference. That implies total work done is the sum of these two things, this plus this. That is P1 A1 V1 dt minus P2 A2 V2 dt. That's due to pressure energy difference. And due to potential energy difference, dmg H1 minus dmg H2. That's the potential energy difference. Now, as per the work energy theorem that we have learned in mechanics 2, work done is the change in kinetic energy. Work done is simply implicated as change in kinetic energy. Delta work done is equal to delta change in kinetic energy. Let us also calculate change in kinetic energy. Kinetic energy is half m v square we have to write. Half m v2 square is bigger because in both the times we assume that the mass dm goes in and goes out according to the equation of continuity. V2 is more. Yeah, there's a little disruption there. So change in kinetic energy is half dm. V2 square will be more than V1 square. That's why I have written half dm V2 square as positive. Half dm V1 square. So now I know the work done due to the pressure energy difference, potential energy difference, their sum. I also know change in the kinetic energy. So I can use work energy theorem that total work done is equal to change in kinetic energy. So what's the equation we can write here is total work done is this P1 A1 V1 dt minus P2 A2 V2 dt plus dmg H1 minus dmg H2 equal to change in kinetic energy. What is that? Half dm V2 square minus V1 square. In both this I have taken dm common. So if you notice, there is a dm here, dm here, and dm here. Only is not there here. So let us divide the entire equation with a divide dm, right? Dividing with dm gives a simplified format. What happens? Let us see. Yes, P1 A1 V1 dt by dm minus here also the same P2 A2 V2 dt by dm plus here dm and dm gets cancelled. Anyway, I will write it for you. dmg H1 by dm, this one minus dmg H2 by dm. Here also the same half dm V2 square minus V1 square by dm. Therefore, all these dm's will be cancelled. Yeah. So we'll get a simplified format. What is that? P1 A1 V1 dt by dm minus P2 A2 V2 dt by dm. Here dm got cancelled, so GH1 minus GH2. Here V2 square minus V1 square by, because there also dm got cancelled. Now we need to know what is this dm is. Dm is a small mass that flown at a given instant dt. So mass can be written like volume into density, that is dm into rho, dv into rho, change in volume. Change in volume can be written like area into change in the length, ds into rho. Displacement can be written like velocity to time, that is v dt into rho. So dmv is this much, area into velocity into dt into v1. So that can be written in this place dm as a1 v1 rho 1 dt, because all the terms in the numerator are there in terms of that ones. To make it more simple, I have written like this. Because anyway, mass enters is mass leaves out, so whatever I write, it's not going to make any difference. Equal to A2 V2 rho 2 dt. So by substituting these values of dm's in this above equation, we'll get a simplified format. What is the simplified format? Let me see. You need to go back and see every time whenever you have a doubt, because I'm scrolling the pages. In the place of this dm, I will write this to make it more simple. Calculate a1 v1 rho 1 dt minus p2 a2 v2 dt. In the place of this dm, I will write this value in terms of 2 so that it will be cancelled. A2 v2 rho 2 dt plus gh1 minus gh2 equal to v2 square minus v1 square by 2. Now so many things will be also cancelled here. A1 V1 will be cancelled, dt dt, A2 V2 dt, A2 V2 dt cancels. So what's the conclusion that we have? That implies P1 by only rho 1 is remaining minus P2 by only rho 2 is remaining plus GH1 minus GH2 equal to V2 square minus V1 square by 2. Let us take all one terms to one side and the two terms to other side. That implies P1 by rho 1 plus GH1. I'll keep this here. I'll get this minus V1 square by 2 to this side. That will become plus V1 square by 2. I will take minus P2 by rho 2 to the other side. It becomes positive. Minus GH2 also becomes positive on the other side. Anyway, on the other side, we have V2 square by 2. So if you simplify this, if you keep on doing for another point also, you may be getting P3 by rho 3 plus GH3 plus V3 square by 2 and so on. Therefore, you can write in general P by rho plus GH plus V square by 2 is constant. If you remember back, potential energy is mgh, but here m is missing. So this is potential energy per unit mass. Kinetic energy is half mv square, that m is also missing. So this is kinetic energy per unit mass. Similarly, this is called pressure head or pressure energy per unit mass. So the theory says the sum of pressure energy, potential energy, kinetic energy per unit mass for a fluid is a constant. That's what the Bernoulli's theorem is. So it's a bit lengthy, so you need to come back and see it again and again. I'll just scroll through once again for your convenience to show quickly that what we are doing, right? So Bernoulli's theorem says for a incompressible, non-viscous, streamlined fluid flow, sum of potential, kinetic energy, and pressure energy per unit mass always remains constant. To prove that, I have considered 2 points x and y with different parameters, like I have mentioned. The relations or comparisons are also written here. So, as per the theory, I have calculated the pressure energy here. I have calculated the potential energy here. I have calculated the kinetic energy here. And I have simply used the work energy theorem. Work energy theorem that work done equal to change in kinetic energy. Simply I have substituted data, concluded. I have written what's the value of that dm is, mass in terms of the given parameters, simplified, and I got a conclusion that the sum of potential energy, kinetic energy, and pressure energy per unit mass is always constant for an incompressible, non-viscous, streamlined fluid flow. That's it. Thank you for watching.